This conference will now be recorded.
So very good evening, student. Today we are going to start a new chapter, that is Oscillations. This is the chapter 14th of 11th standard. So today we'll be learning very interesting lessons on periodic motion, oscillations, vibrations, harmonic, non-harmonic motions, etc. So so far we have learned various type of motion. Okay, I'll just give you some examples like motion of some car in a rectilinear motion or a straight line, motion of a car in a straight line. I'm abbreviating straight line as ST line, ST dot line. So this is one type of motion, rectilinear motion we have seen. These are the things which we have already learned. Then I'll write another type of motion, that is circular motion. Suppose circular motion. So this even in case of planetary motion also similar to circular motion, planetary motion. Okay, and another type like motion which we see during swinging in a swing. So motion in a swing. See, we have seen maybe many other complicated motion, very zigzag motion, etc. in our day-to-day life. We are experienced with various type of motions. But one interesting thing is that each and every motion has their own characteristics. Like some motions are one characteristics I can write. Some motions are repetitive. Motions are repetitive. Even repetitive in nature, and some motion are not. Okay. So in the oscillation, we are going to concentrate the motion which are repetitive in nature. I see among these three examples, the motion in a straight line, if a car goes through a straight road, there is no possibility that it will go forward and come back and forth like that. There is no possibility, or there is no necessity also. There is no necessity. And it is the nature of the motion that when motion in a straight line, it is a one way type, or the motion it may come back, doesn't matter, but at least it will not continue to go back and forth. Okay, this is not the nature of the force and the nature of the motion. So straight line motion or rectilinear motion is not repetitive motion. It is not a repetitive motion. It is not repetitive. Whereas circular motion, you look, if you start from this point A, you go all the way to B and go to C, all the way up to D, and then come back to A. Again, you can start from A, go all the way and come back here. So it is a repetitive motion. It is a repetitive motion. If I just think of and a wall clock, wall clock, see, and I take the hour hand, okay, this hand for the hour, okay. So it actually start from here and goes all the way around this and come back to here. And this has a definite time interval. This has a definite time interval. If it is hour hand, then it will take 24 hours. Okay, 24 hours. I'm sorry, this will take 1 hour. Sorry, I'm sorry. This will take 1 hour. Okay, if it is hour hand, it will take 1 hour to come back to this point. So the definite interval is 1 hour. Again, if I take a minute hand, then it will take 60 minutes to repeat its motion. If I take second, then it will take 60 seconds to repeat its motion. So this is a kind of circular motion. So this is circular motion, and this circular motion is repetitive in nature. Even planetary motion also repetitive in nature. Okay, so this is repetitive in nature. Repetitive. Even in swinging also, the motion in a swing is also repetitive in nature. This is from our practical experience. We know you go front and back, okay, go front and back like that, go back and forth, okay. So that is also a repetitive motion. So this repetitive motion actually are called as periodic motion because they repeat their motion after a definite interval of time. So those kind of motions are called periodic motions. Okay. So I have actually got some examples for you. See, this is swinging back and forth is a repetitive motion. Okay. Then, as I said, planetary motion. So this is motion in a swing. So swinging motion, swinging, and this is planetary motion. So these are all actually repetitive motion. And another one, see, this is the pendulum in a clock, wall clock. This type of pendulum, where in the early days it was so famous, still it is existing. You can see this, like at a particular time after 1 hour, after each 1 hour, this will ring and it will actually go back and forth. It is actually called pendulum, which go back and forth. It goes here, okay, and then come back to here again. It goes either way, okay. Eventually this angular displacement is same on either side, okay. So again it come back to this original position or the mean position. This is called mean position. You can go to here, and then come back to mean position and go here like that. So AOC, suppose E AOB, so it goes back and forth along this AOB path. Okay, this is a repetitive motion. So these kind of motions are called periodic motions. Okay, all right. And what is oscillatory motion? Okay, we'll with this introduction, let us go to specifically what is called periodic or harmonic motion. We'll define now what is called periodic or harmonic motion. Okay, by the way, you might be thinking, sir, why do we need to learn all these periodic, oscillatory, and harmonic, non-harmonic motions, etc.? In our day-to-day life, when we analyze things, basically with the music instruments, so you vibrate some wire inside a vacuum or some most of the instruments, music instruments, you have a vacuum, you are either vibrating a wire or an air column which produces sound of various frequencies. Okay, so music instruments and many other places, actually this oscillations in many practical cases where the knowledge of oscillations will be required. It is not only in music industry. You will be seeing in medical, in the like see the heartbeat is a periodic vibration. Okay, periodic vibration. Okay, so there you need to know what is called vibration, what is the period, frequency, etc. You need to know. In engineering, you need to know. Everywhere it is required. You should have good knowledge about oscillations or vibrations to analyze things like this in our practical life. So that's why it is mandatory, or it is important to learn oscillatory motions and their characteristics, various nature of the oscillatory or the periodic motions. Okay, now we'll define what is a periodic motion. We have somewhat defined already, but still we'll formally define what is called a periodic motion. So any motion which repeats itself over and over again after a regular interval of time interval of time is called a periodic or harmonic motion. I have already given you examples, like a planet moves around the sun in an elliptical orbit or nearly circular orbit. Okay, basically elliptic orbit in planetary motion. Okay, so planetary motion, I'll write, I have already discussed this. So planetary motion, I'll just write the examples as it is. Okay, then the motion of hands of clock, motion of hands of a clock, then the motion of Halley's comet, motion of Halley's comet, Halley's comet around the sun. So the period or the time interval it takes actually 76 years to repeat its motion around the sun. Okay, so these are examples of. There may be many other. Okay, there may be many other like in automobiles the pistons move back and forth. In many engines pistons move back and forth in a periodic manner, that is also a periodic or harmonic motion. Okay, now we'll learn what is called oscillations and what is called vibration. What is the basic difference between vibrations and oscillations? So if a body moves back and forth repeatedly, if a body moves back and forth, sorry, if a body moves back and forth repeatedly, about a mean position, about a mean position. Mean position means sometime equilibrium position. Sometime we can say equilibrium position is actually mean position. Then its motion is called an oscillatory motion. Oscillatory motion. Okay. This can be also called vibrations or vibrations. Since it is repeating after a particular interval of time, then it can be also called harmonic motion. Actually, all oscillatory motions will be harmonic, but all harmonic motion cannot be cannot be an oscillatory motion or oscillation. I'll repeat the sentence. All oscillatory motions are harmonic. Okay, harmonic motions, but but all harmonic motions may not be oscillatory motion. What does this mean? This means that, see, oscillator, when we called oscillation, suppose I have a pendulum. Okay, I have a pendulum. Suppose this is the O position, which is called equilibrium or mean position, where it has minimum energy configuration. Okay, now, and also there is no net force acting over here. Now, when you just pull it this way up to a point, let me draw this with dotted line. So this is one position. Okay, you just pull it and then leave it. So it will come up to here O, and then equally it will go to the other side like this. Okay, it will go to the other side also. So look this, if I say this is B, so this particular object, let us say this is a bob or maybe the pendulum of a clock. When it repeats the motion back and forth, it is going towards A and coming back towards B, back and forth about this O. So A to B, B to A, like that it is going back and forth about O. O is the mean position where there is no force, or it is the equilibrium position of this pendulum. So this motion is called oscillatory motion. This is oscillatory motion. I can give you another example, like in the swing. In the swing also motion, in the swing also an oscillatory motion. Okay, it goes back and forth. So it goes back and forth. Okay, it goes back and forth. Okay, so that's why. Okay, so it goes back and forth. So that's why swinging motion is also an oscillatory motion. And since it is repeating, then it is called actually a harmonic motion, sorry, a periodic motion. Periodic or harmonic, the same, periodic motion. Okay, but this periodic motion, so this periodic motion, it's called either oscillation or just periodic or harmonic motion, because it is going back and forth around a mean position. But suppose, I say the parallel motion, it is also harmonic motion. It is starting about the sun, it goes all the way B, C, D, and come back to here. Okay, but it is not going back and forth. It is not going back and forth. It is just completing one full motion and then again starting from it. So it is actually not going back and forth. So this is not an oscillatory motion. This is not an oscillatory motion. Okay, I can give you some examples of oscillatory motion. So in the actually in the oscillatory motion, you will have two extremum positions about its mean position. Two extremum position means, see, A and B. If you push this object to this point, beyond that it will not go if you leave it here. Okay, beyond this it will not go. So it has two extremum position, OA and OB. These are called displacements from the mean position. So it has two extremum positions and it is confined. Its motion is confined within that limit. Its motion is confined within that limit. So this is, so if the motion is repeating and confined within a limit, that is called actually vibration, that is called oscillatory motion. And see, in the circular motion, this is a harmonic or periodic motion because it is repeating its motion after a particular time interval, but it is not oscillating or it is not moving uh, back and forth about a mean position, and it does not have any extremum or like minimum displacement or maximum displacement. Okay, there is no concept of that. So that's why this is not oscillatory. It is periodic or harmonic, but non-oscillatory motion. Non-oscillatory motion. You have to understand the difference between harmonic or periodic motion. All periodic motions cannot be oscillatory motion, but all oscillatory motions must be periodic, okay, or harmonic. That is what to learn over here. Now you might be thinking, what is vibration? I have understood oscillatory motion, but what is vibrational motion, or what is the vibration? See, oscillatory motion and vibration basically are the same. But what is the difference? See, sometimes vibration, see, oscillations can be very fast, and sometimes it will be very slow. It will be sometimes very fast, and sometimes oscillation can be very fast, and also it can be very slow. So this fast and slow, this actually, these two terms will be well understood if we define a term called frequency. I'm going to define that very soon. Frequency. So when the frequency is very high, so I'll write high frequency oscillation. That means number of oscillations in unit time, per unit time, is more. Okay. See, one complete oscillation, we will say one complete oscillation when an object starting from A goes to B, and then goes to O, again it goes to B, and then comes back in the same path, B to O, O to A. When it starts from A to O to B, and then again it starts from B to O to A. So this is a complete oscillation. This is called complete oscillation. So this is called complete oscillation, or one cycle, one full cycle. So number of full cycle per second is called frequency. Number of full cycles per second is called frequency. So high frequency oscillation is called vibration. High frequency oscillation is called vibration. Okay, vibration. Sorry. High frequency oscillation is called vibration, and low frequency oscillation is called simply oscillation. Okay, so this is what you have to remember. So high frequency oscillation is called vibration. Okay, so we have understood what is oscillation and what is vibration. Now we'll go to the next slide. So here we are discussing what is called a periodic function. Okay, I hope I have given you enough examples over here in the oscillatory motion, like swinging of a pendulum, simply swinging in a swing, and then piston of automobile that goes back and forth, vibration of a string in a guitar or any music instrument. The vibration you see, that is also oscillatory motion. Vibration of string in a guitar. Okay, so these are few examples of oscillatory motions or vibrations. Now we'll learn what is called a periodic function. exactly what is called periodic function. Before we we learn that, let me define what is called period and what is called frequency, etc. See, I have I have a complete oscillation. See, it starts from zero. This is a sine wave. You might be familiar with this. So this goes from zero all the way up to maximum value. This is positive one, say, okay, because sine has value, extremum values plus and minus, okay, plus minus one. So it goes from zero to some values, and then like it increases gradually up to a maximum value. Then it again decreases, and then it crosses the zero and goes to the other side with the same minus one extremum value. This is called extremum. This is actually minimum value. This is the maximum value. So again, after, see, it started from zero, so it takes values and then goes to positive maximum, then decreases and goes through zero, and it goes to the other side with maximum value minus one, and then it actually decreases to zero. So this is a complete oscillation. This is called complete oscillation. And the time it takes, the lowest time it takes to complete a full oscillation, okay, the lowest means smallest time. The smallest time it takes to complete a full oscillation, the smallest time an oscillator takes to complete a full oscillation. Full oscillation. Oscillation is called the time period. Time period. That is denoted by T. Time period is time. It is denoted by capital T. Universally, this notation is actually universal. Whenever we say time period, in any case, we'll denote it by capital T, and its unit is second. Second, okay, either you write S or SEC, okay. So these are all usable notation. So what is time period? The smallest time. See, sometime in the definition you might be seeing that the smallest time interval after which the motion is repeated, or yes, so the time interval after which the motion repeats. See, if this is t one time interval, and then the motion repeats it from here again, and then it goes here, so this is another time interval, so it is another t from here to here, another t, okay. If I just consider the motion, see, if I consider the motion from the maximum value from this point, then one full oscillation will complete. See, from here to here, here to here, it will complete here, okay. So this will be full oscillation, so this time will give you the time interval, okay. Time, sorry, period, okay, time period. All right, so I have defined what is called period, and at the same time I'll define another term called frequency. Period, period is denoted by T. This is time period, better to write time period. Okay, and then frequency, see how many number of full cycles. So number of full cycles, frequency is actually number of full cycles. Number of full cycles, number of full cycle executed, or number of full oscillations executed per second. Per second. In every second, how many full oscillations are happening? That number is called the frequency, and that is denoted by nu. This is nu. Okay, that is denoted by nu, and there is a, see, I'll just complete this. Let me complete this here. So time period, relation between time period and time period and frequency. Okay, so time period is the minimum or the smallest time to have a complete oscillation, have a to execute a complete oscillation, to execute a complete or a full oscillation. I could have written vibration also, doesn't matter. Full oscillation. Okay, now frequency means what? So this is actually time period. Okay, this is time period. What is frequency? Let us say, okay, so frequency, new number of full oscillations per second. Okay, let me consider for a particular oscillations, t is the time period, so t seconds time period. Okay, time period is t second. So in 1 second, how many? So t second means what? So t second means one. Sorry, t second. Yes. So t second means one one full oscillations in t seconds, right? Now, what is the one full? So this is a one full oscillation in t seconds. Okay. Then in 1 second, how many full oscillations will be there? So let me do it in either way. So t seconds, one in t seconds, one full oscillation. So then in 1 second, 1 second, how many? 1 over t. This many will be the number of full oscillations. Full oscillations. And look, we have got the definition of Okay, if you are not understanding, let me do it once again. So suppose for an oscillation, t second is the time period and nu be the frequency. Okay, now we have to find out the relation between t and now we have to find out the relation between t and nu. Okay, this is my agenda now. I know the definition of both. So let us say in t seconds, one full oscillation, because this is the definition of time period. Okay, then in 1 second, how many full oscillations will be there? 1 over t full oscillations will be there. And see, this is actually, see, number of oscillations, that is number of oscillations oscillations per second is the frequency. Is the frequency. So that's why this frequency and time period, they are actually reciprocal of each other. So this t has unit second and nu has unit per second. Per second means per second is given a new name called hertz. Hertz, okay? Hertz denoted by H Z, capital H and small z. It is the number. It is actually after the name of the discoverer of uh, the radio frequency or radio. Okay, so this has unit hertz. Frequency has unit hertz. It is basically having dimension inverse of time. Okay, all right. So now we'll learn what is a periodic function. So a function can be called as a periodic function. Suppose I have a function f of psi. So if the function remains same after a complete, like after a time interval, see, if I say this argument, this is called argument. If this argument is changed to phi prime, and what is the prime? This is psi plus t. Okay, psi plus t. That means, see, I was, suppose f of psi is here. F of psi is here. Now after one time interval, sorry, one time period, this will be here, right? It will be here. If I simply again write f of psi prime, that means f of psi double prime. So f of psi plus 2t. Then I was here initially when f of psi, the value of the function was here. After one time period, the object has shifted to here, but the value is the same. Again, after two time interval, like two time periods. See, one time period is this one, another this one. After that also, see the object will be here somewhere. Okay, it is changing its position, but since it is going integral multiple as a integral multiple of the time period, the value of the function is not changing. Each and every time you look, it is the zero. So it is a zero. Therefore, I can define a function to be periodic when this is equal to f of psi, where n is an integral multiple, integer number. Okay, integer. Okay, it has to be an integral multiple. So okay, you can write that it is an integral multiple. I'll just give you a simple example. It is a sinusoidal wave, right? It's a sine wave. Simply to say it is a sine wave. So I'll write the definition of psi, this function, periodic function. It can be generally written as this f of, this will be f of psi. Okay. So this is actually the definition of a periodic function. Okay, now I'll take practical example like sine theta. If f of psi is if f of psi is sine theta, okay, or okay, f of psi is sine theta. Now if I write f of psi plus capital T, let us say this is radian, so I will not go with time, we'll go with angle. So 2 pi, that means it is sine of theta plus 2 pi, right? So look how this is sine theta itself. So this means it is actually f of psi itself. Okay. If this function is not an angle, if it is in terms of time, if suppose this is f of t is equal to sine of 2 pi n by t, 2 pi n by t. Okay. If this is a function, see after time interval of capital T, so we can write sine of 2 pi n by t plus capital T. Okay, so again, sine of 2 pi by t, actually, just a minute, we are taking an example. F of t, suppose f of t is equal to sine 2 pi t by capital T, sine 2 pi t by capital T. Now when t becomes t prime means t plus capital T. Okay, when this becomes this, so let us say here f of t plus t capital T sine of 2 pi by t, and here it is t plus capital T. Okay, so if we put that over here, look how the function remains the same. See, sine 2 pi small t by capital T as it is, and this will be again 2 pi. So sine theta plus 2 pi, we have seen it will be just sine theta. Okay. So this is actually called as uh, periodic function. Okay, this is called periodic function. Okay. And some functions are harmonic or some functions will be, so the periodic functions which can be repeated like sine and cosine functions are actually called harmonic functions or periodic function, or we can say periodic harmonic function. But sometimes harmonic functions are not necessarily, all harmonic functions are not necessarily periodic, but all periodic functions are not harmonic. So the periodic functions which can not be represented by sine or cosine function are called non-harmonic function. So we will define non-harmonic function. So here it is said that periodic functions which can be repeated by a sine or cosine curve, represented. The periodic functions which can be represented by sine or cosine curve are called harmonic functions. So what are called harmonic functions? The functions the functions which can be represented represented by sine or cosine functions sine or cosine functions are called harmonic functions. Called harmonic functions. Okay. Now all harmonic functions are necessarily periodic, but all periodic functions are not harmonic. The periodic functions which cannot be represented by single sign, or see here I have shown you some periodic but non-harmonic functions. So the functions which are periodic but cannot be represented by a single sine or cosine function. Sine or cosine function. So these are called non-harmonic functions. So here this is a harmonic function, as you can see. Okay, but the function you see over here, these are actually occurring after a particular interval of time. So these are actually periodic. This is actually called rectangular functions. So these are called actually rectangular functions, rectangular wave functions. You can see that. So these are actually occurring after a particular time interval, but these cannot be expressed in terms of single sine or cosine functions. Similarly, this is called sawtooth wave function, and this is another function which is actually periodic but not. So this is called sawtooth wave function. Sawtooth wave function. This is rectangular wave function, and this is some other periodic function, but it is not harmonic because this see these are not represented by single sine or cosine functions, but non-harmonic motion can be represented. Non-harmonic motion or function can be represented by more than one sine or cosine function. Okay, so I'll stop it here for today. Next day, so this was kind of an introduction class. Next class, we'll learn what is simple harmonic motion and related concepts. Okay, so we'll stop it here for today. Thank you for your patience.